Let's solve some Leetcode question today, which is Leetcode 332 Reconstruct Itinerary. So the reason why I'm recording this video is because I was trying to solve this challenge and I've stumbled across brute force solution, which passed before on Leetcode, but it doesn't pass anymore because they added some tests which are much more complex and it just gives you a time limit exceeded exception. I'm going to leave a link in the description to brute force backtracking solution. You can watch it later. So let's read the description of the problem. We are given the array of tickets, and each ticket has a source and destination airports, but the order of the tickets is unknown. So the task is to reconstruct the order that person traveled between the airports. The important thing to notice is that each ticket is used only once and we can't use the same ticket twice. Another thing is that the person always departs from JFK airport. And if there are several solutions, we need to return one with the smallest lexical order. We can immediately see that this is a graph problem. Essentially, we need to find the order in that we need to traverse the directed graph using each edge only once. It's quite a famous problem, by the way. So the example one is quite simple. You can see that we can start at JFK, then we go to MUC, then LHR, SFO, and SGC. But there will be more complex cases like you see in example 2. I actually like this problem a lot because it touches some very interesting concepts. So I'm going to touch on brute force backtracking, and then I'm going to explain what's called a Hierholtzer algorithm. Let's skip to discussing solutions. First, let's briefly discuss basic backtracking solution that I've seen on Leetcode's channel. I'm not going to go into details a lot, and I actually advise you to watch his video before mine. It is very good and covers interesting concepts. You will have better understanding of the optimization I'm going to make. But anyway, so the point of backtracking solution is we are trying to traverse the graph in alphabetical order, and if you find a dead end, we return back and try another branch. First, we build an adjacency list of sources and destinations in a sorted order. You can see I've already built it on the right. Next, if we try brute force solution from JFK node, we see that the first node is A, we try A, we put it into resulting list, but there is nowhere to go from node A, so we mark it as a dead end, and it means we need to go another way. We remove A from the result, we put it back to adjacency list, and we go to node B. Let's remove it from adjacency list and put it into the result. Next node C, let's do the same. Next JFK, next node A, which was back in the adjacency list from before. We finish the algorithm because we know that the result length is number of tickets plus 1, which means that we've traversed all the edges and we can stop the algorithm. So you can see in the solution we had to traverse JFK to A twice. So there is an inefficiency in this algorithm which causes the worst case performance as big O of number of edges to the power of number of maximum flights from one airport. We can actually see that it happens if we add more nodes to node A with some complex paths. Let me show you the code and you will see that the Leetcode doesn't accept the solution. So this is the code solution for brute force backtracking. Let's submit it and you can see that the solution exceeds the time limit on the infamous test case 80. Is there a way to do better? Yes, and it's actually called the Hierholtzer algorithm. It is actually a bit trickier to grasp, but if you understand some interesting concepts of graph theory, it's not very complicated and the code is going to be simpler than brute force backtracking. So the first concept to understand is Euler's graph theorem. I'm not going to go into the math of it, you can easily Google it if you're interested, but the important consequence from that theorem is you can traverse a graph using each edge only once, if and only if the number of nodes with odd number of adjacent edges is not more than 2. Also, those nodes should be the start and finish of the traversal. At first, it sounds a bit complicated, but actually let me give you some examples and you will understand it intuitively. Look at this graph, for example. There are 2 nodes with a number of edges, JFK and A. The rest ones have even. So no matter how you traverse this graph, starting at JFK, you will always finish at A. For example, you can go JFK to B, to C, to A, to D, to E, to JFK again, and then we finish at A. Also, you can notice that if you don't start at JFK, there is no way to traverse this graph using each node only once. So let's look at another example. In this case, all nodes have even number of edges. You can notice that you will always return into the starting node. I actually advise you to try it by yourself. Okay, so the main idea of the algorithm is that when we are traversing and finding a node with no outcoming unused edges, it means that we reached our final destination node and we can move back from this node and get the path in reverse order. What we need to do is, at the end, is just to reverse the resulting path and we will get the answer. So let's keep to the actual algorithm. Let's take the previous example where I demonstrated the brute force backtracking. So let's build an adjacency list the same way as we've built it previously. Let's start traversing our graph. From node JFK, we first go to node A. Node A doesn't have any outcoming edges, so we found our finish node. Let's put it into the result. Then we go to node B. It has outcoming node C. Then we return to JFK. You can see that I already traversed all the paths from JFK, so we can put JFK into the result. Then we pop out, put node C, then node B, and before we finish, we need to put the starting JFK node because it's basically the one we started with. You can see that if you reverse this list now, you will have the correct answer. Let's code our solution for our problem using what we learned just now. Okay, I'm going to start with building adjacency list. So what we are using here is just a dictionary in Python with default value of an empty list. Okay. Okay, we're gonna append each destination. Then what I'm going to do is remember that we need to sort our results in lexical order. So I'm going to sort all the items in my adjacency list, but I'm going to sort it in reverse order. It doesn't matter for the algorithm, but it's just is gonna make code easier and a little bit more performant. I'm going to initialize our result and as an empty list now. Then I'm going to define our DFS function. And the only argument it's going to take is our SRC airport. Okay, then I'm going to take the list of destinations of our SRC airport, and then I'm going to loop through all the destinations, and I'm going to pick next destination. And here is why I sorted our destinations in the reverse order, because popping from the end of array is faster than popping from the beginning. Is like roughly O from 1, but if you do it from the beginning, or big O from 0, sorry, from n. So then I'm going to call DFS for all destinations, and only after that I'm going to append our SRC node. So if you try to run this code through different examples with your pen and paper, you will see that basically this while loop always for every destination which doesn't have any for every source which doesn't have any outcoming destinations is gonna skip and just append the SRC, and if there are destinations, is going to loop through them. Then the rest, what we need to do is just call our DFS, and remember we always start at JFK, and then what we need to do is just to reverse our result, and in Python you can do it like this. Okay, I'm going to submit the code. Hopefully all good. Yeah, it is accepted. It is fast, so yeah, and it is working. Cool. So that's the end of the video. Hope you liked it, and hope it makes it clear. Thank you very much for watching, and bye bye.